Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I would like to show you very quickly two or three useful circuits with which we can replace the 555 timer and why we might want to do so. The 555 timer is a very popular integrated circuit, but it does have a little bit of disadvantages that sometimes we just cannot live with. So I recently needed a timer. I recently needed basically a pulse generator with a variable duty cycle, and I needed a circuit that can work with powered from a simple battery, a lithium battery that has anywhere between 3 volts and 4.3, 4.2, 4.3 volts, depending on what lithium battery is. And well, I hit the problem with not being able to use a 555 timer, so this is why I have done a bit of research and a bit of experimentation, and I have managed to come with a few circuits that I want to show you today. First of all, before we dive into today's circuits, please allow me to thank the sponsor of this video, PCBWay, and at the same time announce to you something that you might find to be good news. They are currently organizing their 6th project design contest, and you can participate too. They have 2 themes this year. You can choose to create an electronic project or a mechanical one. Apply and upload the necessary files until 15 January 2024. And if you're one of the lucky winners, you'll find that on 8 March 2024. You can find all the details and the rules of the contests in the contest webpage. In order to help you building the electronic circuits or the 3D objects that you might need to enter this contest, they can assist you with their PCB manufacturing services, PCB and components assembly, semi-dest stencils, as well as 3D printing, injection molding, or even CNC machining. Both the link to PCBWay.com and their contests are in the description. Thank you very much, PCBWay, for sponsoring this video. Good luck with the contest if you choose to participate. And now let's get started with the circuits that I want to show you. So, like I said in the beginning, we would like to replace the 555 timer, or rather use something different. Why? Well, we have at least 4 reasons to do that. One is the fact that the 555 timer officially must have at least 4.5 volts in order to work. Maybe unofficially it works with lesser voltage, but I don't think we can rely on him working with less than 4.5 volts. This is particularly a problem when we have a circuit that needs to be powered by 2 standard batteries, 1.5 volt battery each, or a lithium accumulator that has anywhere between 3 volts when it's completely discharged and 4.2 or 4.3 volts when it's completely charged. Obviously, we cannot employ a 555 timer because we cannot rely on him. So there are better options, and the simplest and cheapest one is to use an open collector comparator, namely 393 or 339. The difference between them are small. The 393 comparators, they come in a pair in a chip, and 339 it's a quad comparator, so a chip contains 4 of them. The advantage from a working voltage point of view is that they can go down to 2 volts. So they are guaranteed to be able to work down to 2 volts, which is very good because it makes it so that we can power these sort of circuits from pretty much any kind of battery. The second advantage, which is sort of related to the first one, is the opposite, meaning the maximum recommended working voltage. For 555 timer, it's 16 volts. For these open collector comparators, it's 36 volts, so double that. This makes it possible for us to create timers even with higher working voltages, like with, I don't know, 24 volts power supplies or something like that. Something that we could not do with the 555 timer. The third reason is the price. The price is twice or even 3 times better for the cheapest 393 comparator, which is an AS393, compared to an A555. Now, it is true that, technically speaking, we are comparing products made by different manufacturers. The NA555 is made by Texas Instruments. The AS393 is made by Diodes Incorporated. However, as far as I'm concerned, it really doesn't matter, because when I pick a component, unless I have very good reasons to pick a certain component from a certain manufacturer, I will take a look at the price and I will choose the smallest price. And when it comes to simple integrated circuits like these, you know, it definitely doesn't matter whether we go with a cheaper version or a more expensive version, because ultimately the circuits are the same and the quality is pretty much the same. So the 555 costs, the cheapest 555 costs about 50 cents a piece if we buy it in small quantity, or about 21 cents if 21 cents a piece. That's euro cents, by the way, not dollars. If we buy larger quantities, like 50 or above, 250 or above or so. Well, the cheapest 393 open collector comparators are 3 times less or even just twice less. So in low quantities they are 18 cents. That's basically 3 times less than these 45. And in larger quantities they get down to about 10 cents a piece, which is still twice less than some 20 cents a piece. Okay, so the price, of course, matters, not when we buy just 10 pieces or so, because then it doesn't matter. But, you know, if we want to buy a larger quantity in advance, because after all, we are trying to prepare right now for the future when we might not have access to these components, well, then the solutions that we choose matter, because then investing in a component that is not quite so versatile and it costs more than another component might just not make any sense. And speaking of versatility, the fourth and last reason that we might want to not choose a 555 timer, by the way, I miscounted these. So the fourth and last reason is that an open collector comparator is universal. Okay, so as opposed to a 555 timer that can only be a timer and can only work as a timer, an open collector comparator, which looks like this, can be used as a timer, like I will show you in a few moments, or they can be used as a simple comparator in another circuit where we want to compare two voltages and do something about them, or who knows in how many other places we might use such an integrated circuit. I recently created a linear accumulator charger that at the core has a quad channel comparator just like this. It wouldn't be impossible to create a linear power supply as well. So basically, if we buy comparators and we are able to use them in many ways, we are at an advantage versus buying 555 timers only for timing circuits and other components for other things. Okay, so technically speaking, if we look inside the 555 timer, we will basically see a couple of comparators and a bistable circuit. Now, this basically means that in order to use anything else than a 555 timer, we need to basically recreate what the 555 timer has inside of him. And so let me show you the simplest circuit, which basically emulates a 555 timer and works identically the same. Let me just make a print screen and so I can draw you a few things on the screen. So this circuit essentially works the same as a 555 timer, meaning we have a capacitor here that is being charged through two resistors in series, R1 and R4. Okay, so when we are charging this, we are charging this like this. And we also have a voltage divider. I've set it to have two identical resistors, but it doesn't have to be, they can be different. And we have a first comparator that literally compares the voltage from this voltage divider, which is basically, it's going to be a constant voltage that's proportional with it's going to be a fraction of the supply voltage. Okay, and it's going to compare it with the voltage across this particular capacitor. When the capacitor is so when the circuit is initially off, the capacitor is of course discharged. When we power this circuit up, then the capacitor will start to charge. Initially, since the plus input, which is officially called a non-inverting input, but I like the plus and the minus terms a lot better because they are clearer. Initially, this has a bigger voltage than the minus input, so the output of this comparator, which I feel the need to remind you, the output is just a collector of bipolar transistor that's found inside the chip. Okay, the output is left floating. The output is connected to this particular point here. Okay, so this capacitor will be able to charge up until it reaches the voltage across him reaches, you know, the voltage on the plus input of the comparator. Then the comparator basically flips from one logic to zero logic, meaning this particular transistor is gonna be turned on hard, and he's gonna pull down this. Okay, so far this PNP transistor was completely off because he didn't have enough emitter base voltage to be turned on. But now that the op-amp will pull his output down to the ground and will make a short circuit with the ground, basically two things will happen. The first thing that will happen is that this point here with that goes to the plus input of the first comparator, this point will go down to the almost to the ground. It's not going to be to the ground, it's because we still have this voltage here, this emitter base voltage of the PNP transistor. But basically, instead of having half the supply voltage here, we will very soon have about 0.7 volts, give or take. Okay, and at the same time, this point here will also be dragged down, which means that this capacitor will first of all, this resistor R1 will be short-circuited to the ground, so he will not matter for us anymore. He will just generate a current that is basically wasted, but anyway, there's not much that we can do about it. And this capacitor will start to discharge, basically, so we will have a current flowing from him through this resistor and then down to the ground, and he will start to discharge. So we will see something like this on the screen. Well, I mean, the voltage on the capacitor. Okay, and then when the voltage drops below this 0.7 volts, give or take, the whole thing flips around once again, and the capacitor charges again, and discharges and charges, and so on and so forth. So with only these few components, we have recreated basically how a 555 works in astable mode. And because the voltage at the output is on this output here is not quite a rectangle, it's not quite a square wave, we can use a second comparator, which we have anyway, because at least if we use LM393, we have two comparators in the package, right? So we can use this comparator to basically take this reference voltage and this output from the first comparator and generate a nicer square wave on his output. Of course, since he also has an open collector output, we need to pull him up, the output up with a resistor. And this is pretty much how everything works here and what we have done. Of course, now we are free to choose all sorts of values for these components. We are free to choose whatever ratio we want here for R2 and R5. We are no longer forced by those three 5 kilo ohm resistors inside the 555 timer. Also, we have basically with this circuit we have the same disadvantage, just like with a similar circuit made with 555 timer, meaning that since we are charging this capacitor through both resistors in series, R1 and R4, but we are discharging him only through R4, then we will at best have 50% duty cycle. We cannot get lower than 50% duty cycle, okay? We can get higher, but we cannot get lower than that. So that may be a problem or may not. I'm just mentioning this so that you are fully aware of this limitation that again exists in 555 timers as well. Now, before I move to the next circuit that is a little bit better than this, let me show you some waveforms. So first of all, let me show you a simulation of this circuit. Okay, I have simulated this earlier before actually making him on a breadboard. So with blue we have the voltage on the capacitor. With red we have the voltage on the first output of the first comparator, and as we can see on the positive edge we have we have a waveform that looks like the voltage on the capacitor, so it's not quite square wave. However, with purple we have the output of the second comparator, which is it looks a lot closer to a square wave, right? Okay, and in practice this is what I have seen. So with some components values I got 222 kilohertz, and the waveforms look like this. And funny thing is, like on the breadboard, if we remove this capacitor and we only allow the parasitic capacitances of the breadboard himself, we can get up to almost 1 megahertz of frequency. I mean, not that we would actually be able to use this, but anyway, at least from the first comparator, we can generate this waveform of close to 1 megahertz. So yeah, if we can, if we have any use of this, then we can definitely work with this. Now, for an improvement, we can essentially make a trick, basically. So here we have the same circuit, just like before. There's nothing changed as far as the principle of working. The only thing that is changed is that this resistor here is very, very small. I've put a 100 ohm resistor and up here a 10 kilo ohm resistor. I'm sorry for coughing from time to time. I'm a bit sick right now, so it's gonna take a while until I get better. Anyway, if we make this resistor very small, then we will make the discharging of this capacitor very fast. So the whole waveform of this capacitor will look a lot more like a triangle, like a sawtooth, okay? It's not gonna be a perfect sawtooth because we would need to have constant current and anyway, but it's gonna be a sawtooth, okay? No, something like a sawtooth. And it's gonna be good enough for us so that with the second comparator, we can do something else. We can connect his minus input to this capacitor as well, just like the first comparator. And the second, the positive input, we can feed this with a voltage, okay? Because technically speaking, the capacitor will be able to charge up to half the voltage, half the supply voltage in this particular configuration with R7 and R11 identical. Of course, you can choose to change their values and therefore you will change the voltage here. And the capacitor will be allowed to charge up to that voltage, okay, until it's discharged. So we can have a voltage here on the second, on the plus input of the second comparator that can go from about 0.7 volts up to whatever the voltage is here. And based on that, we can basically have more or less fixed frequency but variable duty cycle output. Okay, which is something that we cannot do with the previous configuration, and it's definitely something that we couldn't have done with the 555 timer. Okay, and I'm not gonna show you the simulations. I'm just gonna show you directly the practical results. So I've used some components to get me a 108 kilohertz signal, and as you can see here, the frequency is pretty much constant. I was playing with that trimmer that you know, gives a reference voltage to the second comparator, and based on that we can clearly see that we can generate variable duty cycle square wave. Now it's true that in the beginning it's not so much of a square wave, it's a bit rounded, but anyway, it is good enough. This is 190 kilohertz. Obviously I changed some values for those RC timing components, but again we have more or less constant frequency and variable duty cycle based on whatever voltage we have there, which is pretty good. And I've also done another test with 460 something kilohertz. This is a bit pushing, but anyway, it's not impossible, to put it this way. By the way, the official 555 timer maximum frequency is 500 kilohertz, so the same that I used here. There are variants of 555 timers that go up to 1 megahertz and even up to 3 megahertz, but those are much more expensive. And most of the time, they don't really make much sense. I mean, I don't know when we might want to have honestly more than 500 kilohertz. I don't see any particular use case for that. At least not from such a simple circuit. If we need higher frequencies, then we most likely need a more sophisticated waveform generator. Okay, so this was the second circuit, and the third circuit that I would like to show you. I have tested, but I haven't filmed because it didn't make any sense. The monostable circuit. Basically, the monostable circuit has one stable state, and it switches to an unstable state for only a very short period of time. And this can be done very, very easily by just having the same voltage divider that sets a reference voltage for the minus input of the comparator, and on the plus input we can have a capacitor in parallel with a resistor. Initially, of course, they will have 0 volts across them, so the comparator will be turned down low, right? Because the voltage on the minus is going to be higher than the voltage on the plus, so we're going to have 0 logic on the output. However, if we use a push button here from the positive supply rail to the capacitor, we will basically be able to instantly charge this capacitor and make this comparator switch from 0 logic to 1 logic. And then when we release the finger from the button, this capacitor will discharge through this resistor in parallel with him, and based on the RC timing constant and whatever voltage we have set here as a reference, you know, we will have a shorter or a longer time for this comparator to stay in 1 logic on the output. And then when the capacitor will be discharged too much, the comparator will switch back to 0 logic and will stay there until we push again on the push button. So this is how a very simple monostable circuit can be created. And of course, we don't necessarily need to have a push button here. We could also have a PNP transistor that acts like a switch that is being commanded by another circuit from afar. Anyway, there are endless possibilities starting from this configuration. Okay, so this was pretty much it. Personally, I think that it's worth thinking about not buying and not using 555 timers anymore, since they are very limited in their scope. They can only be timers. Like I said, open collector comparators are universal. They don't have to be only these models, 393 and 339. There can be any other models that you can find on the market. It's up to you. So yeah, thank you very much for watching. I hope this information was useful to you. I will definitely use these circuits in the future for my projects, so stay tuned. The month of September wasn't so good for me, but I hope the month of October will be better in terms of being able to build more circuits and more devices. So thanks a lot for watching this video. You can help by subscribing to the channel and hitting the like button if you've enjoyed this video and you want to see more. I will see you next time. Bye bye.